Today I'm going to show you everything about how to work with exponents. So that means we're going to cover all of the basic exponent rules. We're going to talk about where exponents come in order of operations, and how to deal with negative exponents and exponents that are fractions. So if keeping track of all of the exponent rules confuses you, you're definitely in the right place. I want to let you know that there are lots of timestamps in the description of this video. So if you're looking for something in particular about exponents, feel free to skip around and go straight to the section you want to. So the first thing we're going to talk about is, what are exponents? There's no difference between exponents and powers. Sometimes people think that they're a different thing, but they mean exactly the same thing. So we could just as easily be asking, what are powers? So exponents are also known as powers. When we talk about exponents or powers in algebra or math in general, what we're talking about is a shorthand way of expressing repeated multiplication of one thing by itself. So what does that mean? Well, let's say, for example, that we have this expression, 4 to the 3. The number on the bottom, 4, is called the base, and this little number on the top right is called the exponent. And when we have a base raised to an exponent, what this tells us is that we want to multiply the base by itself however many times the exponent says. So because this is 4 to the 3, it means multiply 4, the base, by itself 3 times, because the exponent is 3. So this is the same thing as 4 times 4 times 4, because we're multiplying 4 by itself 3 times. So the reason that we use exponents in math is because if we want this value, 4 times 4 times 4, it's a lot easier to write it as 4 to the third instead of writing out this whole thing 4 times 4 times 4 every time. You'll also see a more generalized example, a to the n, which just means multiply a by itself n times, in the same way that 4 to the 3 means multiply 4 by itself 3 times. So whatever number you have for n, or the exponent, that's how many times you multiply the base by itself. So this would be a times a times a dot 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 times a, and this would be done n times, because n, the exponent here, is how many times we want to multiply a by itself. Now keep in mind that there are a bunch of different ways to read an exponent. So for example, if we go back to this first problem, 4 to the 3, we could read this as 4 to the 3, 4 to the third power, 4 to the third. So all of those ways of reading this exponential expression are correct, but usually the simplest way to read this is 4 to the third, or this expression here as a to the n. Now, one other thing about how to read exponents, you can always just say the base to the exponent like we did 4 to the third, but there are a couple of exponents that also have special names. So for example, if you have this, you could definitely read that as x to the 2. But because the exponent of 2 is so common, we give it a special name, and we can also read this as x squared. So whenever you see an exponent of 2, you can just say squared instead. So you can read this correctly as x to the 2 or x to the second, but more conveniently, you can also read it as x squared. Same thing with x to the 3 or x to the third. The exponent of 3 has a special name called cubed, so we can also read this as x cubed. And you can remember that because when you think of a square has 2 sides. If we draw a square, we have one side and then the other side, which we multiply together to get area. So that's why we say x squared, because there's 2 sides and we have an exponent of 2. If you have an exponent of 3, we say cubed because if we draw a cube like this, we have 1, 2, 3 dimensions, right? Length, width, and height that we multiply together to get volume, and that's why we say x cubed when the exponent is 3. So why are exponents used in math? Well, like we talked about before, they're just convenient abbreviations for something that would otherwise be difficult to write. So for example, if we wanted to express x being multiplied by itself 7 times, without exponents, we would have to show that multiplication as x multiplied by itself 7 times. So 1, 2, 3, 4, 5, 6, 7 times x multiplied by itself. But once we have exponents and we're able to use them to abbreviate this x multiplied by itself 7 times just becomes x to the power of 7, or x to the 7th. In math, you always want to write things in the simplest way possible. And obviously, x to the 7 looks a lot simpler than x multiplied by itself 7 times written out like this, which is why we like to use exponents. But which one of these do you think is simpler? Is it simpler to say 2 to the 3rd or 8? Well, these are actually equal to each other because remember 2 to the 3rd is 2 times 2 times 2, 2 multiplied by itself 3 times, which 2 times 2 would be 4 multiplied by this last 2 that we didn't use yet, and then 4 times 2 is 8. So 2 to the 3rd is the same thing as 8, but which one would you rather see in your math problem? Well, it would definitely be the 8, because 8 is a lot simpler than 2 to the 3rd. So exponents are really helpful when we're talking about simplifying something like x to the 7th, but when it comes to whole numbers like this, oftentimes it's simpler to write out just the number rather than writing it in exponential form, because you'd much rather have 8 than 2 to the 3rd. So this is really the primary reason why we learn exponents in the first place and why exponents are useful in math. They can just make our expressions and our equations a lot simpler, which will make them easier for us to solve. Now we're going to talk about how to simplify exponents and how to solve exponent problems. And in order to do that, you're going to need this collection of basic exponent rules. And there's quite a few of them, but we're going to go through each one to make sure you understand how to use all of them. So the first one is called the 0 rule. And this is what you use whenever the exponent is 0. And the rule here is that anything raised to the 0 power is equal to 1. So in other words, if I say x to the 0, because the exponent is 0, this will be equal to 1. When I say 2 to the 0, that will be equal to 1 because the exponent is 0. If I even have something like this, ab raised to the 0 power, this looks more complicated, but again, because the exponent is 0, this is equal to 1. So no matter what the base is, whether the base is x, whether it's 2, or whether it's ab, like this, the value is always 1 because the exponent was 0. The only exception to this is 0 to the 0, which honestly is a whole different discussion. But just know that anything else raised to the 0 power is 1. That goes for variables like x, or the product of variables like ab, or constant numbers like 2, and even negative numbers. For example, negative 2 to the 0 power would also still be 1, because regardless of the base, as long as the exponent is 0, the value is 1. The next rule is called the 1 rule. And just like the 0 rule, This is the rule that you use when the exponent is 1. So in the same way, we could have x to the 1, and this is going to be equal to x, because the 1 rule says that anything raised to the power of 1, anything where the exponent is 1, the exponent won't change the value of the base, so the result is always just whatever you had for the base. So x to the 1 is still just x. 2 to the 1 is still just 2, or something like this. ab to the 1 is still just ab. So notice how we always just get the base back. And this is even true for 0 to the 1. 0 to the 1 is still 0. This also works for negative numbers, like -2 to the 1 is still just -2. And the reason this works is because, remember, the exponent tells you how many times to multiply the base by itself. So for example, 2 to the first power is just telling you multiply 2 by itself 1 time. And you might think that that means actually 2 times 2, right? If I multiply 2 by itself 1 time, maybe that's 2 times 2. But this would be multiplying 2 by itself 2 times. This would be 2 squared. Multiplying 2 by itself 1 time is just 2, which is why you always just get the base back when you raise something to the power of 1. Now the 0 rule and the 1 rule are fairly straightforward. This next rule is where things start to get a little bit trickier. This one is called the power rule. And a lot of times people remember it by thinking of a power to a power. And when you use this rule, you'll be multiplying exponents together. I'm going to talk a little bit later about when you add exponents together. So with power rule, you have something like this. For example, x to the a, and then you're raising that to the power of b. Now I know this might be confusing at first, but the next example I'm going to do is going to make it a lot easier. I just wanted to tell you that when you have a base, x, and then an exponent, a, and then you raise that whole thing to another exponent, you multiply these powers together. So when you multiply a times b, you're going to get ab. So this is the same thing as x to the ab, because the exponents get multiplied together. Here's the example that will show you why this is true. Let's say we have 2 to the third, and then we're raising that to the power of 2. If you just use the power rule for exponents to simplify this, you'll look at this and say, I need to multiply the exponents, so 3 times 2 is 6, which means that this is 2 to the 6th power. But even if you didn't know power rule, here's how you would figure this out. You would first simplify what's inside the parentheses, which goes back to your order of operations, and I'll talk about that in a few minutes. So you always do what's inside the parentheses first, and 2 to the third power is 2 times 2 times 2. 2 multiplied by itself 3 times. So when I do 2 times 2, right here, I get 4, and then I still have 1 2 left. So then when I say 4 times 2, I get 8, which means what's inside the parentheses is 8, and now I just have 8 to the 2, or 8 squared. When I do 8 squared, that's the same thing as 8 times 8, which I know is 64. So 2 to the third squared is 64. And what I would see is that if I do 2 to the 6th power, let's do that up here. So 2 to the 6th power is 2 multiplied by itself 6 times. So 2 times 2, 3, 4, 5, 6. And here's the simple way to do this. I can take 2 times 2, and I know this is 4. I can take this 2 times 2, and I know that that's 4. And I can take this 2 times 2, and I know that that's 4. So this 2 times 2 times 2 times 2 times 2 times 2 can be simplified to 4 times 4 times 4. Now, when I do that problem, 4 times 4 is 16. So I end up with 16 from these two, and I just have the 1 4 left over. So 16 times 4, and 16 times 4 is equal to 64. And remember, 64 was the value that we got before here, which is how we know that our power rule worked, because we used power rule to simplify this to 2 to the 6th power. And when we did that arithmetic out, we got 64. Or we just calculated it one exponent at a time without power rule, and we did 2 to the 3rd to get 8, and then we took 8 squared to get 64, and we got the same answer using both methods. The next one is the negative exponent rule. And this one can be a little tricky, but there's actually a simple way to think about it. So this is the rule you use when you deal with negative exponents. For example, let's say that we have x to the negative a. So our exponent is negative because the exponent is negative a. The base is x, and the exponent is negative a. The first thing you want to do whenever you have a negative exponent is immediately change it to a positive exponent, because positive exponents are just easier to deal with. So the way that you change this to a positive exponent is you think about x to the negative a as a fraction. So before you panic, here's what I mean when I say fraction. So whenever you have something like this, it's clearly not a fraction. You can change it into a fraction just by putting this whole thing over the denominator of 1. Now it's a fraction, but we haven't changed the value of it at all, because when you make the denominator 1, you're just dividing by 1. But dividing by 1 doesn't change the value of anything. For example, if I take 3 divided by 1, it's still just 3. Same thing here, x to the negative a, all divided by 1, is still just x to the negative a. So if you don't have a fraction, you can always make it a fraction just by making the denominator equal to 1. Okay, so now here's what the negative exponent rule says as far as how to make this negative exponent a positive exponent. What you want to do is you want to take this whole thing, whatever the exponent applies to, so you want to take the base and the exponent, and you want to move that down to the denominator. When you do that, the exponent will change from negative to a positive. So what you get when you do that is you get the x to the a in the denominator, and we were just able to change the exponent from negative a to positive a because we moved it from the numerator to the denominator, and that's how you make negative exponents positive exponents. All you have to realize here is that we still have the 1, so we still have the 1, and we still have a 1 in the numerator because this x to the negative a is just like multiplying 1 by x to the negative a. It doesn't change that value. So when you pull x to the negative a out of the numerator and you put it into the denominator, you're not left with 0 up here. You're left with 1. Now, it's redundant to write 1x to the a because multiplying by 1 doesn't change the value. So we really don't need this 1 down here. We can just say that x to the negative a is the same thing as 1 over x to the a. So if you take another example, let's say 2 to the negative 3, that's always just the same thing as 1 in the numerator and then 2 to the positive 3 in the denominator. So we just move this whole thing down to the denominator in order to make the exponent positive instead of negative. Now here's the other interesting thing. I can also go the opposite way. So for example, if I have 1 over 2 to the negative 3, I have a negative exponent in my denominator, but I can make it positive just by moving it to the numerator. So this is the same as 2 to the positive 3. So I just moved it from the denominator up to the numerator, and it made the exponent positive. So whenever you use the negative exponent rule, just remember that if you have a negative exponent in the numerator, you can make it positive by moving it to the denominator. And when you have a negative exponent in the denominator, you can make it positive by moving it to the numerator. The next one is the product rule. So the product rule for exponents. And with this one, what you're going to want to do is add your exponents. So remember before we had the power rule, and with the power rule, we multiplied our exponents. But with the product rule, we're going to add our exponents. So for example, you use the product rule when you have something like this. Let's say you have x squared multiplied by x cubed. So these two things are multiplied together, which we know because they're right next to each other. We could have a multiplication dot in there, or they could be multiplied together like this inside parentheses. But either way, we're multiplying x squared by x cubed. So a problem like this one is when you use product rule. Notice that the bases are the same. So the base of x squared is x, and the base of x cubed is x. So because the bases are the same, we can multiply these together using the product rule, and when we do that, we add the exponents. So the base stays the same, but the exponents get added. So this is raised to the exponent 2 plus 3, which is going to be equal to x to the 5th. If you had something like 3 squared multiplied by 3 to the 4th, you would use product rule here too, because the bases are the same, and we're multiplying these two terms together. So because we're multiplying, and because the bases are the same, we can use product rule, and the result is to keep the base the same, 3, and then add the exponents. So 2 plus 4, and that'll give us 3 to the 6th power. So 3 to the 6th power by the product rule is the same as 3 squared times 3 to the 4th, because with product rule, you add the exponents. You can't use product rule if the bases are different. So if I, instead of x squared times x cubed, had a squared times b cubed, I can't use the product rule to multiply these two together because my bases are different. One base is a, and the other base is b. If you have different bases but the same exponent, this is a slightly different property of exponents, but sometimes it trips people up. If I have a squared times b squared, my bases are still different, so I can't use the product rule. But when the exponents are the same, I can rewrite this as ab squared. But this is only when these terms are multiplied together. If you have a squared plus b squared, or a squared minus b squared, you can't do this. Again, we're talking about the product rule, where product means multiplication. So this applies to terms that are being multiplied together. So if we have a squared multiplied by b squared, we can put the ab together and put the exponent outside of it. Now this is the last one, and it's similar to the product rule, but this one is called the quotient rule. So product rule, remember, said product, which is multiplication. Quotient rule has quotient, and remember, quotient means division. Remember how with product rule we added the exponents? Well, quotient rule is where we subtract the exponents. You use quotient rule when you have something like this. Let's say you have x to the 4th power divided by x to the 2. So this is a fraction with x to the 4th in the numerator and x squared in the denominator. And in this case, when you simplify this, just like product rule, because my bases are the same, I have base x for both terms, my base will stay the same. But the exponents simplify by taking the exponent in the numerator, 4, and subtracting the exponent in the denominator, 2. So 4 minus 2 is 2, so this is equal to x squared. And there's another way to think about this. Let's write out the terms that we have here. So x to the 4th is the same as x times x times x times x, and x squared is the same as x times x. Well, remember with fractions, we can always cancel terms that are common to the numerator and denominator. So here, if we cancel out 2 x's from the denominator, that means we're canceling out 2 x's from the numerator. And notice then that the only thing we're left with is 2 factors of x in the numerator, which we could simplify to just x squared. So that's why the quotient rule works, because you're basically just canceling common factors. Now, what about this one? What about when you have x squared in the numerator and x to the 4th in the denominator? Well, you can follow the exact same process we did before. Because the bases are the same, the base is still x. Then you take the exponent in the numerator and subtract the exponent in the denominator, so we get 2 minus 4. Well, 2 minus 4 is negative 2, so this is x to the negative 2. This is where the negative exponent rule would come into play. So we have x to the negative 2. If we want to make that positive, we just move it to the denominator, and we say that this is the same as 1 over x to the positive 2. So 1 over x to the positive 2 is the result. There are 2 ways to tackle this. The first way, where we take the exponent in the numerator and subtract the exponent in the denominator, like we did in this first example. Or we can do a little shortcut here so that we don't have to make this change at the end in order to make the exponent positive. What you can do instead is recognize that the exponent will be positive wherever we have the larger exponent. So when we have x squared over x to the 4th, 4 is larger than 2. So what we can do then is, instead of sticking with our numerator minus denominator rule, we could put the x wherever the larger exponent exists. The larger exponent is in the denominator, so we put the exponent in the denominator. And then for the exponent on that base, we say 4 minus 2. We always take the larger number minus the smaller number. 4 minus 2 is 2. And then we just put a 1 on the other side of the fraction. So you can do it that way also. Okay, so what if our bases are different? All these examples are where the bases are the same. If we have different bases, for example, a to the 4th over b squared, we can't simplify this because our bases are different, so we're not able to apply quotient rule. But like product rule, there is that one exception where the bases can be different, but the exponents can be the same. So if we have a squared over b squared, like that product rule, because the 2 is applied to the a and the b separately, we could also write this as a divided by b and pull the exponent outside the parentheses. Now, I know all these rules can get confusing, but the one thing that I would say is that if you're ever not sure, one of the best tricks that you can use for simplifying exponents this way is to write out the exponents in their long form, like this. So if you're ever not sure, for example, about x to the 4th over x squared, if you're supposed to subtract the exponents or add them or multiply them, you can always write out x to the 4th like this, or you can write out x squared like this, and then you can cancel factors and reassure yourself that this is x squared. Or for example, with product rule, where you have something like x squared multiplied by x cubed, and you don't remember if you're supposed to add the exponents or multiply them, try writing them out. So x squared, you know, is x times x, and you know that x to the 3rd is x times x times x. And then when you look at this, you see that you have x multiplied by itself 5 times, which you know is x to the 5th. So that tells you that when you have these multiplied together, you're supposed to add the exponents, because 2 plus 3 is 5. So if you're ever unsure, just try writing it out like this, or like we did for this problem, and that might help you figure it out. Now just a quick note about order of operations and PEMDAS. So remember that order of operations tells you to start first with parentheses, then exponents, and then here you have multiplication, division, addition, and subtraction. I want to focus on the first part, parentheses, then exponents. So with exponent rules, a lot of times you're going to have something inside parentheses and then an exponent outside the parentheses, like in the last quotient rule example where we had AB squared. Or if you had something like 3 plus 4 cubed. Or maybe you'd have something like x squared y to the 4th power. Your order of operations tells you that you always want to simplify what's inside the parentheses before you go applying the exponents. So you always have to remember when you start an exponent problem, if there's anything inside the parentheses that you can simplify first, you definitely want to do that. So in these two examples, this one here and this one, there's nothing that we can simplify inside the parentheses. So we could then go ahead and apply the exponent, and this would come out to a squared over b squared. This would come out to x to the 8th, y to the 4th. But this here can be simplified. So we would definitely want to do what's inside the parentheses first. We would say 3 plus 4 is 7, and we would get 7, and then apply the exponent of 3. We would never want to say that this is 3 cubed plus 4 cubed, or some other application of the exponent. We always want to simplify what's inside the parentheses first. What about when exponents are negative? Well, we talked about the negative exponent rule before, which told us that when we have x to the negative n, that's the same thing as 1 over x to the positive n. We just move it to the denominator in order to make the exponent positive. We also talked about the reverse of that, where if we have something like this, where we have a negative exponent in the denominator, we just move it to the other side of the fraction, the numerator, to make it positive. So wherever you have a negative exponent, you can just move it to the opposite side of the fraction, and the exponent will become positive. So that's what we do when exponents are negative, and that's the easy way to get rid of negative exponents. But what about when the base is negative? This is really important. So when I have something like negative x to the n, that means I have a negative base. My base is negative x because it's inside the parentheses, which means that the n applies to both the negative sign and the x. In fact, you can even think about this as negative 1 times x. And when you have an exponent outside of the parentheses, the exponent is distributive, which means it distributes to both the negative 1 and the x, or to the negative sign and the x. So this is the same thing as negative 1 to the n times x to the n. The exponent gets distributed to both the negative 1 and the x. So I have a negative base where I have to distribute the exponent to that negative sign. This, however, is not at all the same thing. This is not a negative base because I don't have parentheses around my negative sign, which means that the exponent n only applies to the x. It's basically the same thing as saying this. I have x to the n power, my base is a positive x, and this negative sign just gets applied after the fact. So let's see what that looks like. So if, for example, I have negative 2 squared, I do have a negative base because I have parentheses around the negative 2. So this is the same thing as saying the entire base, -2, times -2, because this says multiply -2 by itself 2 times, since the exponent is 2. Well, -2 times -2 is a positive 4, because my negative signs cancel, and 2 times 2 is 4. But if I have -2 squared, because there are no parentheses, the 2 does not get distributed to the negative sign, which means that I basically have parentheses around the 2 squared. I always do my operations inside the parentheses first, so 2 squared is 4, and this is equal to -4, and then when I take the parentheses away, I get -4. So I got a totally different answer, -4, when I had no parentheses around the negative sign than I did +4 when I did have parentheses around the negative sign. The last thing I want to talk about before we work an example is when exponents are fractions. It's important to realize that fractional exponents are just a different way of writing roots or radicals. So, for example, x raised to the 1/2 power, where the exponent is 1/2, is exactly the same thing as the square root of x. It's just a different way of writing these values, but these two things are equal to one another. In the same way, x to the 1/3 is equal to the third root of x. So this is the square root of x equal to x to the 1/2 power. This is the third root of x, or the cube root of x, equal to x to the 1/3 power. There's a couple really interesting things to know about fractional exponents. First, if you want to convert a fractional exponent into a root or vice versa, you can separate the numerator and the denominator. So here our numerator is 1 and our denominator is 2. The numerator always remains as an exponent on the base. So here, under our square root, we have x to the 1 because the numerator was equal to 1. The value for the denominator becomes the root. So 2 is the special case where this is just the square root. But here with 3, it's the cube root, which is why you see the 3 out here, because that's the denominator and this is x to the 1st power inside the root. So therefore, x to the 1/4 is the same thing as the 4th root of x to the 1st, which means that if we have x to the 2/3 and we want to convert that to a root, we get our square root here, our x goes underneath it, the numerator is a 2, so that stays on the base, this is x squared, and the denominator is a 3, so this is the third root. So that's how we convert between roots and fractional exponents. But there's one other important thing to say about exponents which are fractions, and that is that we have to remember the power rule from earlier. Remember, the power rule said that if we had x to the a and then raised to the b, that we multiply these exponents by each other, and this is x to the a times b, and these are the same thing. With fractional exponents, we have to remember that the fraction 2/3 is the same thing as 2 times 1/3. So we could rewrite x to the 2/3 as x squared and then raise that whole thing to the 1/3. So these two values are exactly the same because by the power rule, we multiply these two exponents together to simplify this, and we get x to the 2 times 1/3. Well, 2 times 1/3 is 2/3, so we get x to the 2/3. So if it helps you to simplify your problem, which it often does, you can always separate exponents like this by putting the numerator here on the inside and just keeping the denominator here on the outside. So let's put everything we've learned into practice on one really tough example. Let's say that we have the fraction -4 x cubed y to the negative 1, and then we square that whole thing, and that's multiplied by 5x cubed y to the negative 2, and that whole thing is raised to the 0 power. And then we want to divide that by 2x to the 4th y, all raised to the 3rd power. Remember that we have these rules, and you always want to apply the rules in this order. So first the 0 rule, then the 1 rule, then power rule, then negative exponent rule, product rule, and quotient rule. Think about it as an order of operations specifically for exponents. Now, speaking of order of operations, remember we always want to try to simplify inside of our parentheses before we go into applying our exponent rules. Well, for us, there's nothing to be simplified inside the parentheses. We can't simplify negative 4x cubed y to the negative 1. We can't simplify 5x cubed y to the negative 2. And we can't simplify 2x to the 4th y. So we can't do anything inside the parentheses, which means that we can now move on to applying our exponent rules. So the first thing we want to do is the 0 rule. And we do that first because that can knock out something really quickly. Remember that when we raise something to the 0 power, that it's equal to 1. So what we see here is that we have this whole value in parentheses, 5x cubed y to the negative 2, and the whole thing is raised to the 0 power. Remember from before that it wouldn't matter what was inside these parentheses. We are raising the entire thing to the 0, which means that that whole term is going to be equal to 1. So what we can do is we can say that this whole thing is equal to 1. But remember that multiplying something by 1 doesn't change its value at all. So multiplying by 1 here isn't going to have any effect on the rest of the numerator, so we can get rid of that completely. Now there's nothing else that's raised to the 0 power, so we want to go on to the second rule, the 1 rule, and see if anything is raised to the power of 1. We've got this y to the negative 1 term, but we're only looking for things that are raised to the power of positive 1. That's the 1 rule. So we can't apply the 1 rule to y to the negative 1. We could only apply it if it were y to the positive 1. So there's nothing to simplify there, and we can say that we've done this rule, the 0 rule, and the 1 rule. Now what about the power rule? Remember that the power rule is a power to a power, or raising one exponent to another exponent. Well, in our case, that means distributing these exponents on the outside across everything inside the parentheses. Remember that exponents are distributive when we have all multiplication inside our parentheses. And here we do. We have negative 4 multiplied by x cubed multiplied by y to the negative 1. So it's all multiplication, and we can distribute the 2 across each term. Same thing here. We have 2 multiplied by x to the 4 multiplied by y. It's all multiplication, so we can distribute the 3. In order to do that, we want to remember that anything that doesn't have an exponent, like this negative 4 and the 2, the implied exponent is a 1. That kind of comes from the 1 rule. So now when we apply the power rule, remember that the power rule tells us to multiply exponents, which means we want to multiply this outside exponent across all the exponents inside the parentheses. So here our negative sign is inside the parentheses, which means the negative 4 is a negative base, and that negative sign gets included. So we want to say negative 4 to the 1 times 2, multiplying those exponents, multiplied by x to the 3 times 2, multiplied by y to the negative 1 times 2. And then in the denominator, we want to say 2 to the 1 times 3 times x to the 4 times 3 times y to the 1, because again, we have an implied 1 there, times 3. So when we simplify, we get negative 4 to the 2. We get x to the 6th, because 3 times 2 is 6, -1 times 2 is -2, so we get y to the -2. And then in the denominator, we get 2 to the 1 times 3. 1 times 3 is 3, so 2 to the 3. 4 times 3 is 12, so we get x to the 12th. And 1 times 3 is 3, so we get y to the 3. So that's power rule applied. Now we want to apply the negative exponent rule, which remember we do for any of the negative exponents that we have by moving that term from the numerator to the denominator or vice versa. So in this case, our only negative exponent is here with y to the -2. So we just want to move that to the denominator in order to make it positive. So we'll have -4 squared x to the 6th, and then we're going to move that y to the -2 to the denominator. So we have 2 cubed x to the 12th, y cubed, and then here our y now to the +2 because it's in the denominator. And that's the negative exponent rule because now all of our exponents are positive. Then we move on to the product rule, which tells us that when we have like bases, we add the exponents. So here we have y to the 3rd multiplied by y squared. We know that product rule allows us to add those exponents together. So this becomes y to the 3 plus 2, or y to the 5. So we can go ahead and write this as y to the 5th power. Now there's no other values in the numerator or the denominator where we can use product rule. So we finished that one. But now we have quotient rule. And with quotient rule, remember that when we have like bases across the numerator and denominator, we subtract the exponents. So here we have x to the 6th in the numerator and x to the 12th in the denominator. Remember that the term is going to stay with the largest exponent. So because 12 is greater than 6, that means that we're going to end up with a positive exponent in the denominator. So what we want to do is subtract the value in the numerator from the value in the denominator. So let's move over our y to the 5th a little bit. And now we're going to want to say 12 minus 6 here in the denominator because the exponent in the denominator is larger. And that gets rid of x to the 6th in the numerator. So 12 minus 6 then is 6. So we're left with x to the 6th power in the denominator. Now that's quotient rule done. We've done all of our exponent rules. We just need to simplify our constants. So here we have -4 squared. The -4 is inside the parentheses, so this is a negative base, and we do have to apply the exponent to the negative sign. So this is telling us to multiply -4 by itself 2 times. So this is the same thing as -4 times -4, which is positive 16, because the negative signs cancel, and 4 times 4 is 16. And then in our denominator, we have 2 to the 3rd, which remember is 2 times 2 times 2. And if we have 2 times 2 times 2, we know that 2 times 2 is 4. 4 times 2 is 8. So we get 8. And then we have x to the 6th, y to the 5th. And remember, whenever you get to the end, you always want to make sure that there's nothing else you can reduce. In this case, we see that we have 16 in the numerator and 8 in the denominator, which means we can factor out an 8. So we know that 16 is the same thing as 8 times 2. And because we have an 8 in the numerator and the denominator, and because everything in the numerator is multiplied together and everything in the denominator is multiplied together, we can cancel those 8s, and we're just left with the 2 in the numerator. So then our final answer is 2 divided by x to the 6th, y to the 5th. I hope that video helped you, and if it did, hit that like button, make sure to subscribe, and I'll see you in the next video.